Welcome back, everyone. Today we're diving deep into a paper that really caught my eye, one that explores just how vulnerable those machine learning models we rely on every day really are.
It's a fascinating area, isn't it? This paper tackled adversarial machine learning, specifically these black box attacks.
Black box attacks, yeah. The paper's premise is really intriguing. Imagine you're like a hacker, but you've got absolutely no inside knowledge of the AI you're trying to target. Can you still trick it?
And the answer, surprisingly, is often yes.
It is. That's what's so unnerving.
Yeah.
So for our listeners, can we break down this black box idea a bit? It's like trying to pick a lock when you don't even know what kind of lock it is.
Right. You're completely blind to the inner workings, no clue about the model's architecture, the training data, anything. All you have is the ability to feed it inputs and see what output it spits out.
And the goal is to make it mess up, to misclassify something without knowing how it's making its decisions in the first place.
Exactly. This paper focuses on crafting adversarial examples. These are inputs like images that have been, well, tweaked ever so slightly, so subtly that a human wouldn't notice, but these changes completely throw off the AI's judgment.
Like that example they give in the paper, modifying a stop sign image so the AI reads it as a yield sign. Kind of scary when you think about self-driving cars, huh?
Oh, absolutely. That's precisely the danger this research highlights. Real-world consequences could be pretty serious.
Okay, so these black box attacks, they're not just theoretical, they're doable. But this paper doesn't stop there. It actually lays out a method for doing it right.
That's right. They have a two-step strategy. First, the attacker trains their own WNAI, a substitute model, to mimic the target AI's behavior.
So like creating a spy to learn the enemy's secrets.
A good analogy. And then they use this substitute model to generate those sneaky adversarial examples that trick the original AI.
Clever. They call this technique Jacobian-based dataset augmentation. I know our listeners are familiar with Jacobians, but maybe we could give a quick explanation of how they come into play here.
Sure. A Jacobian matrix basically tells you how sensitive a function's output is to changes in its inputs. So in this case, it's revealing how much the AI's prediction changes when you tweak the input features, even slightly.
Ah, so they're using that sensitivity information to train their substitute model, focusing on those spots where the target AI is, well, most ticklish.
Exactly. They're basically reverse engineering the AI's vulnerabilities. And here's where it gets even more interesting. The paper shows that the substitute's overall accuracy isn't as crucial as you might think.
Really?
Yeah. What matters most is how well it replicates the target AI's decision boundaries. You know, those thresholds where it flips from classifying something as A to classifying it as B.
So even, say, a simple substitute model could do the trick if it nails those decision points.
Precisely. They even used models as simple as logistic regression to create successful adversarial examples.
Wow. And they actually put this to the test against real AI systems, didn't they?
They did. They targeted image classifiers hosted by, well, some big names out there, MetaMind, Amazon, Google. And in some cases, their adversarial examples achieved misclassification rates of over 80%.
It's pretty unsettling, considering those systems are probably being used in the real world right now. Makes you wonder how secure all these widely deployed AIs really are.
It definitely raises some serious concerns.
So if an attacker can pull this off, using just a substitute model, is there any way to defend against these attacks?
Well, the paper looked at some existing defense mechanisms, things like adversarial training and defensive distillation, but they found those aren't totally effective against this black box approach.
Why not? What makes them fall short here?
Well, most of those defenses focus on what we call gradient masking. They try to smooth out the AI's decision boundaries or hide those gradients that attackers rely on.
So basically making the AI less sensitive to those tiny input tweaks.
Right. But here's the catch. The attacker's substitute model isn't subject to those defenses. It still has those sensitive gradients that can be exploited to create the adversarial examples.
Ah, I see. So the substitute learns how to poke at the original AI, even if the original has been hardened?
Exactly. They bypass the defenses because they're playing a different game, so to speak.
This research really exposes a blind spot in AI security, doesn't it? We've been so busy fortifying the AI itself that we haven't considered someone building a whole other AI to figure out how to crack it.
That's a very good point. And it raises a crucial question. Where do we go from here? Do we need a whole new way of thinking about AI security?
It's definitely food for thought, especially as AI becomes more and more integrated into, well, everything. But let's maybe take a step back for a second and recap what we've covered so far. We've established that these black box attacks, where you don't need to know how the AI works internally, they're a genuine threat. And they work because even commercial-grade AIs are susceptible to these carefully crafted adversarial examples.
Right. And we've talked about how attackers can essentially build a spy AI, a substitute model, to figure out the target AI's weaknesses. This lets them make those adversarial examples that slip right past existing defenses, which mostly focus on hiding gradients or smoothing things over.
You've also made it clear that how accurate the substitute model is, well, it's not as important as how well it captures those critical decision points of the original AI. Even simple models can do the job.
Exactly. And the big takeaway from the paper is that we need a new paradigm for AI security, one that moves beyond just focusing on those tiny, infinitesimal changes to the input. We need techniques that make AI fundamentally more robust.
Robust to a wider range of, well, adversarial shenanigans. This has been a great start to our deep dive. I think we've laid a solid groundwork for understanding these key concepts and the big challenges ahead in AI security. But let's dive even deeper, shall we? Next, I want to explore the specifics of how they craft these adversarial examples, and also what kind of defenses might actually hold up against them.
So you're interested in the nitty-gritty of how these adversarial examples are actually made. Well, the researchers in this paper, they dug into two main algorithms, the Goodfellow algorithm and the Papernot algorithm.
Yes. Those names definitely ring a bell. But could we break down how those algorithms differ? Like, what are the trade-offs involved in choosing one over the other?
Sure. The Goodfellow algorithm, you might also hear it called the fast gradient sine method. Well, it basically adds a little nudge, a perturbation to the input in the direction of the cost function's gradient. In simpler terms, it's pushing the input towards a region where the model is most likely to trip up and misclassify it.
So it's like finding the quickest path to fool the AI, exploiting those specific input features it's most sensitive to.
Exactly. It's efficient computationally, but the downside is that the perturbations can be more noticeable. Someone looking closely might spot them. Now, the Papernot algorithm, it takes a more targeted approach, I'd say. It focuses on tweaking specific input features, the ones that have the biggest impact on the AI's decision, based on something called adversarial saliency.
So instead of just nudging everything a little, it's like zeroing in on the AI's Achilles heel.
You got it. This results in perturbations that are much subtler, harder to detect. But the trade-off is that it takes more computational muscle to pull off. So it really boils down to what the attacker prioritizes. Speed versus stealth.
Fascinating. So they've got a whole toolkit for crafting these adversarial examples,
Yeah.
each with pros and cons. Now, the paper also talks about oracle queries. I know this is a key part of their attack strategy. Could you explain what those are and why they matter so much?
An oracle query is basically when the attacker gives an input to the target AI and peeks at the output label. Each query gives them a bit more information about the AI's decision boundaries. The catch is, if they make too many queries, it could tip off the target system that something fishy is going on.
Like a burglar trying to crack a safe quietly. Too much fiddling, and the alarm goes off.
A perfect analogy, and the researchers really emphasize that trade-off. They showed that their attack can work even with a limited number of oracle queries, making it much more realistic, for a real-world attack scenario.
Makes sense. Now, let's talk about those calibration experiments they did. What were they trying to figure out there, and what did they learn?
Well, they were very thorough, I'll give them that. They tested all sorts of things to optimize their attack. One big one was the architecture of that substitute model. Turns out it wasn't as important as you might think. Even simple architectures like good old logistic regression work surprisingly well.
So it's not about building a perfect replica of the target AI, but more about finding a model that mimics its weaknesses.
Exactly. They also looked at how long they trained the substitute model. More training isn't always better, apparently. There is a sweet spot where the substitute captures those crucial decision boundaries without getting too hung up on the limited data from the oracle queries.
Efficiency is key. Keep the queries low, training time short, and stay under the radar.
Exactly. And they also compared different methods for making those adversarial examples, the Goodfellow versus the Papernot algorithms. Both actually worked pretty well, achieving high misclassification rates.
So attackers have options, different tools for different jobs.
Right. But maybe the most important finding, and this is where it gets a bit scary, is that their attack worked against AI systems from multiple companies, not just one. MetaMind, Amazon, Google, they all fell for it. It shows this isn't just a problem with one specific platform or type of model.
That's a bit of a wake-up call, isn't it? Makes you think about all those AI systems out there doing important things and how vulnerable they might be. But what about defenses? Did the paper offer any hope there?
They did talk about some existing defenses like adversarial training and defensive distillation, the ones that rely on gradient masking, like we discussed earlier. The problem is they don't really hold up against this black box attack.
Right, because the substitute model, it's not playing by those rules. It can still find and exploit those sensitive gradients.
Precisely. The paper argues that we need to shift gears, move beyond this focus on infinitesimal perturbations, those tiny tweaks. We need to start thinking about defending against finite perturbations.
So make AI models that are tougher, more resilient to bigger, more noticeable changes, changes that maybe even a human could spot.
Exactly. This might mean coming up with totally new training methods, different model architectures, or even ways to spot and neutralize those adversarial examples before they can do any harm.
It's a whole new frontier in AI security, isn't it? Lots of challenges, but also, I imagine, a lot of exciting research opportunities. But before we get too far ahead of ourselves, maybe we should take stock of where we are. This research has definitely highlighted some serious vulnerabilities in AI systems. Even those commercially deployed ones, doing real-world work, are susceptible to these carefully crafted adversarial examples. And it all boils down to this idea of attackers being able to create a spy, AI, a substitute model, to probe for weaknesses.
Right, and the key takeaway is that simply masking gradients or smoothing things over, that's not enough anymore. We need a new approach to AI security, one that focuses on building truly robust AI models that can handle a much wider range of, well, let's call them attacks.
Attacks that could come from anywhere, using techniques we haven't even thought of yet. This has been a truly eye-opening discussion. It's clear that the field of AI security is evolving rapidly, and this research is a crucial step in understanding the challenges we face.
Absolutely. This paper is a real game changer, isn't it? It's not just pointing out the problems, it's pushing us to rethink AI security from the ground up. We can't just keep bolting on defenses. We need to bake in robustness from the very beginning.
Couldn't agree more. This research is a call to arms, really. We need to get serious about developing AI models that can stand up to these attacks, these manipulations, whatever form they might take. The work they've done here, it's going to have a big impact, shape the future of AI security research for sure. Well, it's certainly given us a lot to think about today. This deep dive into black box attacks has been, well, fascinating and a little bit unnerving, to be honest. Thank you so much for walking us through this groundbreaking research. Your expertise has been invaluable.
My pleasure. This kind of work, it really showcases the ingenuity out there, both in terms of the attacks, A&D, the defenses. It's a constant race, a cat and mouse game,
Right.
to build AI that's both powerful and secure.
And that's a race we can't afford to lose, can we?
Mm.
Well, on that note, big thanks to all our listeners for joining us on this deep dive into the world of adversarial machine learning. It's a complex field, but we hope we've shed some light on, well, how these attacks work, why they're so concerning, and what we might be able to do about them. Until next time, keep exploring, keep asking those tough questions, and as always, keep diving deep.